7.4 because that's kind of like the oddball section of the chapter, so we'll do that one at the end. But all of what we're doing with 7.1, 7.2, 7.3, and now 7.5, so think about it like solving systems, writing systems, and now graphing systems of inequalities. This is all a build up to 7.6, which is something called linear programming. So linear programming requires you to first write a system of constraints, graph them like we will today to find what's called a feasible region, like solutions that work. And then we're going to test the vertices of our feasible region to see where we can maximize or minimize something, and that will answer our question. In order to find the vertices of our feasible region, those are the intersection points around our shaded region, and I'll show those to you today. Well, then you're solving systems in order to find those intersection points. So we're kind of putting together all of our skills. Okay, remember we got to be building those and making sure we feel confident. So just really quickly with graphing inequalities, we already kind of reviewed this in our warm-up. Make sure if you need to, you write something down. You've got to be focused on whether your line is solid or dashed. Generally, with our linear programming problems later in the chapter in 7.6, it's going to be solid, so it's going to have the or equals to. But it is possible to graph an inequality with a less than or greater than. And then the other thing to always remember, and this will be really important to linear programming so you find what we call that feasible region, the solutions that work, is the shading. So I will write down here the shortcut for y equals mx plus b. Okay, and that's the one Sierra gave us in the warm-up. Okay. And that shortcut is just that if you have a y greater than mx plus b, you would shade up from the y-intercept. If you have a y less than mx plus b, you're going to shade down from the y-intercept. Okay, rather than memorize like a whole bunch of shortcuts for other functions, because things kind of get a little bit tricky there, and for other forms for the equation of the line, because you have to pay attention to positives and negatives, what I'll say is for all other functions or forms, whether they're lines or not lines, then I would use a different strategy for deciding where to shade, and that's called using a test point. Okay, and the point you pick to test, the only rule about that point is that it should not be on your line or curve. So pick a point not on the curve. If you pick a point on your graph, those are the points where the two sides of the function are equal, and you know it's either solid or dashed, whether you include them or not. But what you want is a point where you'll have something greater than or less than, so not equal, so that you can see if that's a true statement or a false statement. Okay, so you pick a point that's not on the curve. It can be anywhere on the graph, okay, as long as it's not on the curve. You're going to plug in for x and y. And then after you plug in for x and y, one of two things will happen, like as you look at your inequality. Your inequality will either be true or false. Where you shade depends on whether that point was true or false. So if it's true, it's part of the solution, and all the areas that we're shading are part of the solution. So you should shade where the point is. So like you'll be able to say like in this part of the graph, this point worked, the inequality was true. We'll see this in our example. This point should be shaded, so I'm going to shade over here and everywhere else that graph is, okay, where that area is. If you plug in a point and you don't know if it's going to be a right point or a wrong point, if you plug in a point and the point is bad, it comes out false. That means that point should never be shaded because it doesn't work with the inequality. So the point is not shaded. So you could even do that like with a line where like I might test the point over here on the sideboard in quadrant 4. Well, this would come out to be false. So like this point should never be shaded. So I have to shade on the other side of the line. So that's using a test point. My first example I'm going to do is one where we haven't graphed these shapes in a while. So let's do this one. We're going to graph the system of inequalities, and we're going to find the vertices, which I haven't talked about yet, but I'll talk about those once we get a graph down. Okay, so we're going to graph this system of inequalities, which means, as soon as I see a system of inequalities, I'm thinking about, all right, solid or dashed, and I'm thinking, don't forget to shade. Right? That's different than just graphing a line or graphing a function. Okay, as you're writing these down, x squared plus y squared is less than 1. Does anybody know what shape that is when you have an x squared and a y squared, Sierra? That is a circle. So we're going to look at graphing a circle. And I'm going to make a little side note to myself. This circle is going to be dashed. I am a big person who, I often forget to pay attention to shaded solid or dashed. So I end up having to erase my graphs a lot. Okay, so I sometimes mark it down so I remember. Does anybody know what the next one is going to be? Y less than or equal to x minus 2 quantity squared? Parabola. That is a parabola. Excellent. And this parabola, because it has the or equals to, remember Josh's rule, this is going to be solid. So just really quickly for the circle, I know it has been a while since we've seen a circle. So this may be the equation for a circle that you saw in geometry. It looks like x minus h quantity squared plus y minus k quantity squared equals r squared. Okay? And in that equation of the circle, h and k are like your left, right, up, down shifts, like they've always been. So this is your center point, and then the square root of this number over on the other side, that's your r, that's your radius. So looking at my equation, what must be the center of my circle? It must be a 0, 0. And what is my radius? 1. Yes. The square root of 1 is 1. Probably like an easy thing for a lot of us to forget is like if it was x squared plus y squared equals equals 4, don't forget that the radius is not 4, the radius is 2, the square root of 4. Right? Because it's equal to r squared. Okay, so I'm gonna draw myself a little coordinate plane over here. Oh, and I'm gonna change this one. Sorry, I forgot to change it in my notes. It's supposed to be -1. If you want to change your parabola. Okay, so center is 0, 0, and then to graph the circle, you basically just count like up 1, right 1, down 1, left 1, right? And then you just try to draw a round shape. Okay, don't forget when you're drawing it should be dashed. Okay with that so far? Okay, how can I graph my parabola? Think back to function yoga. You see it squared, so you know it's a beautiful parabola. Where is your parabola being moved? Right one. Okay, so we just move the vertex right one. Okay. So I'm going to take what used to be at 0, 0 is now at 1, 0. And then you should remember like the basic movements for a parabola, that like the first point, you know, if you put in 1, then you get 1 back out. Y equals x squared. And if you put in 2, then you get 4 back out. So those are like your basic movements. The only time you would have to change those if you have vertical stretch or shrink. Okay. So I could go up 1, right 1, and up 1, left 1. And if I wanted to, I could go up 4, right 2, up 4, left 2. Right? That would give me some nice points on my parabola without having to make a table of values. So that's kind of nice to know. And this one should be solid. Now, you guys have nice paper and pencil, so you can do some kind of shading, but the smart board is not really great for shading. It gets really messy. So I'm just going to go back here at the end and decide, like, where should I be shading? Okay? So for both of these both of these graphs, a nice point for me to test would be at the origin. Okay? So I'm going to test the point 0, 0 because it's not on either graph. So for the circle, I put 0 in for x and 0 in for y, and I get something like 0 is less than 1. Is that true? Oh, yes it is. 0 is less than 1. I would rather have $1 than $0 because 1 is more. Yes? Okay, so that means that the circle 0, 0 in the middle, it should be shaded. And so I would be shading inside the circle. Now the parabola cuts that into 2 parts. Am I shading this little section or this larger section? So now I'm going to test my parabola. I'll put 0 in for x and y. That's 0 is less than or equal to, that comes out to be 0 minus 1, so negative 1 squared is 1. True or false? Also true, right? We've already decided that. So then, again, 0, 0 should be shaded. So now my shaded region is that larger piece. I wouldn't shade over here as my like overlapping section because those points right there wouldn't work for the parabola. They would make it false. Okay, questions about my graphing? Okay, now remember, on the homework, it's going to ask you not only to graph them, but to also find the vertices. So just really quickly, some information about vertices. Vertices are like the corners of your shaded region, but you only want the corners that are intersections of 2 graphs. So in this image, I'm going to call this V sub 1, and this is going to be V sub 2. I have 2 vertices because my parabola and my circle are intersecting at 2 spots. Do you know what those 2 points are exactly? Yeah, because we plotted each one of them when we were graphing the lines, right? So I can say V sub 1 is 0, 1, and V sub 2 is 1, 0. So when you're thinking about your answers tonight, you want to have the picture with the shaded region, but we also want to be able to go the step further and say, like, what are the corners where around the shaded region our graphs are intersecting? Okay. Now, sometimes they don't intersect at nice points. Like you didn't plot each of them on the lines or the curves. So then it's like, where is that intersection point? That's when you solve a system, right? You can treat this like x squared plus y squared equals 1. You can treat this like y equals quantity x minus 1 squared, solved by substitution or elimination, okay? And you would find the two answers. Now we have just about 4 minutes left, so I'm going to go fast on the next example. I would say you probably don't want to write it down. You just want to kind of like follow along and see my process, because you might have some that are made up of lines, okay? All right, I'm going to graph these in different colors, okay? And remember, you certainly could take the time to change them all to slope-intercept form, but I'm going to be real honest, that's something you aren't going to want to do in linear programming. So I'm going to use my intercept method. For this first one, I'm going to do in blue. X-intercept is 6, Y-intercept is 3. Plot those. See, I only have 5 right there. Solid or dashed? Solid. Got a line. Maybe think about where you should shade. I could use 0, 0 as a test point. Is 0 less than 6? Yeah, so I would be shading down on that line, okay, towards 0, 0. Okay, second one, I'm going to do in green. X-intercept is 5, Y-intercept is also 5. So I can plot a 5 on the y-axis and a 5 on the x-axis, solid or dashed? Dashed. Check 0, 0 because it's not on the line. That's an easy one to check. Is 0 less than 5? Sure is. Okay, so I'm shading down. So I'm thinking about where my actual shading is. It's kind of like in this V, right? Obtuse angle. Okay, last one I'm going to do in red. Is it okay that my x-intercept is going to be at 5/3? Yeah, that just means in between 1 and 2, right? And what? Be careful here. What's your y-intercept? -5. So I would go down 5, 1 2/3, solid or dashed? Solid. Check 0, 0. Is 0 greater than or equal to 5? No. So now 0, 0 over here should not be shaded. So I will be shading on the other side of the red line, away from 0, 0. And when I think about where all of my overlap is, that's in this little kind of section here. This is what we would call unbounded. It just keeps going forever. But there are 2 vertices where the red and the blue intersect and where the blue and the green intersect. So if you graph really fast and you can't tell where your intersection points are, then you can set them as systems. So like the red and the green are the last 2. X plus y equals 5. 3x minus y equals 5. Okay. And that's going to be what? Are the red and the... Is that the green was my middle? I forgot. I'm last check. Oh, I'm doing green and blue. The red and the green is not a vertex. I should be doing right here is the blue and the green. So that's x plus 2y was my blue equals 6. My green was x plus y equals 5. Notice when you solve that system for the vertex, you don't need to like worry about the inequality. I can multiply that whole one by -1. So I get y equals 1. If y is 1, I could plug it back into the x plus y equals 5, and x is 4. So vertex 2 is 4, 1. Okay, you'll need to solve the system to find vertex 1 on your homework.
Oh. Wait, does that